Bueno, buenas. I'm going to speak in Spanish. There should be simultaneous translation. So, but let us know if there's any problem, please. Just to introduce everyone. Bueno, bienvenidos a todos los que están acá, bienvenidos a la UDD, aquellos que no son de acá y a los que sí, bueno, qué bueno que nos están acompañando. Esta es la Semana del Biodiseño y la Industria organizada por ExploraTec. ExploraTec es el área, el centro de exploración tecnológica interdisciplinaria de las facultades de Diseño e Ingeniería, que trabaja combinando fuertemente esas dos disciplinas, pero también involucra a una serie de otras disciplinas y de hecho eso se conecta con la charla con la cual comienza esta semana hoy día en torno a la arquitectura y la bioética, ¿verdad? Entonces, les decía que ExploraTec tiene una agenda muy fuerte en torno a enseñar tecnologías avanzadas a estudiantes de pregrado. Si bien trabajamos fuertemente, como les decía, con la ingeniería y con el diseño de manera interdisciplinaria, esto involucra necesariamente otras ramas como la arquitectura, como la bioética y en ese sentido tenemos un honor, es un lugar común decirlo, pero efectivamente es un honor tener a 3 instituciones internacionales en realidad presentes a lo largo de esta semana. Hoy día nos está acompañando el California College of the Arts como institución y también el Biodesign Challenge. Y a lo largo de la semana hay diversas actividades con el socio, las socias principales nuestras que son de la Universidad de California, en su sede de Davis, con la cual estamos haciendo esta semana de manera conjunta. Semana que tiene una actividad clave el día miércoles, es la actividad prominente desde el punto de vista de la interacción entre el diseño y la ingeniería. Es un seminario internacional que parte a las 3 de la tarde. Los aprovecho de invitar en esta apertura que tenemos hoy. También para el día miércoles y posteriormente va a haber una actividad que les vamos a estar contando a lo largo de la semana el día viernes, ¿sí? Así que para esta semana que hemos denominado del biodiseño a la industria, la idea es poder centrarnos en cómo la subdisciplina emergente del biodiseño está conectando el trabajo, el desarrollo, la elaboración, la manufactura con nuevos materiales de origen biológico, cómo está conectando esa arena de trabajo con la ingeniería. Entonces viene a tocar una tecla muy relevante para la universidad, para ExploraTec, para la interdisciplina en general basada en la tecnología. Y para eso, hoy vamos a estar hablando de aristas que cruzan muy de lleno a este tema, vinculados a la arquitectura y a la bioética. Y para eso voy a presentar a los 4 charlistas que nos acompañan. En la pantalla al menos vemos a Margaret Ikeda, Master of Architecture de Berkeley, cofundadora del Architectural Ecologist Lab de California College of the Arts, ella. Vemos también a Ivan Jones, también Master of Architecture de Berkeley, cofundador también de Architectural Ecologist Lab del California College of the Arts. Y nos va a estar acompañando Dan Grashkin también de la institución del Biodesign Challenge. Él fue fundador y es exdirector del Biodesign Challenge, una iniciativa global donde se hacen converger diversos trabajos en torno al biodiseño. Dan es MFA del Brooklyn College. Así que sin más, vamos a dar paso al inicio de esta semana con estas invitadas y esta conversación.
So, can you hear us? Right now, we can't hear the room, so
Yes,
I'm not
we
sure.
we can hear you, Margaret and Ivan.
Okay.
So-
Okay.
Great.
Okay.
So we'll just start.
We're going to share the screen. Well, thank you for having us. Before we share the screen, and you will see the work, not us. Thank you so much for having us here for your seminar. Just early this morning, Nagar Kalantar was, we were planning to present together with our colleague Nagar, but she got a call late last night about family, so she can't, an emergency that she isn't able to make it, but we will be here to represent her work too. So I'm going to share the screen. Can you see that well? Okay, great.
Yes.
So again, thank you for having us here today. We are very happy to be sharing the space with Dan because much we'll explain later, but Biodesign Challenge has been a very important aspect and platform for us for the kind of work that we're going to be sharing with you today. So our talk is called Biodesign Discoveries Through Collaborative Making. And I'm Margaret Ikeda, that was described before, but I am an associate professor of architecture at California College of the Arts in San Francisco. And I'm a co-director of the Architecture Ecologies Lab.
Yes, and I'm Evan Jones, and together with another colleague, we co-founded the Architecture Ecologies Lab at CCA through the Architecture Division.
And Nagar Kalantar is associate professor of the digital. She is a co-director of the Digital Craft Lab, and she works. She teaches both in the interior design and the architecture division. So together, we present this work from the Digital Craft Lab and the Architecture Ecologies Lab. So a little background into our school. We are very happy to be we wish we could visit, but we are happy that we get to share the Pacific Coast with you and your country. We are located in San Francisco. You can see the backdrop of the San Francisco skyline. The CCA is a campus that was started in 1907. In 1906, there was the big earthquake in San Francisco that destroyed much of San Francisco. And the year after, a German cabinet maker decided to form a campus that would educate students both in the theory and practice of the arts, and started that campus in Oakland, which is on the East Bay. In the 80s, CCA bought this campus, this building right below, and started the architecture and design program. And so this last year, we consolidated both campuses. And in the image on the right, we're very excited because on the far right, a new campus is being constructed as we speak. And in the next fall of 2024, that campus will be open. And along with that new campus, we have a new president, David House, so it promises to be a very exciting new era for CCA starting next year. So that's the context of our college. We're in the south of San Francisco. And a little bit about the Architecture Ecologies Lab. Our work really is at the intersection of architecture, ecological research, and public engagement. And our interest is not so much to have a lab, a particular lab within the school, but we like to think of our lab as the Bay. And so the lab functions as we create these speculative studios or speculative electives, and in yellow are places where we have led those studios. But in pink are the locations out of those studios has evolved quite naturally research project, ecological research. And so in the bubbles on the top is a float lab. It's about the size of a car. And it's floating in partnership with the Port of Oakland, really exploring floating architecture that could scale up to floating homes. That's been in the water for 4 years. And then we have the lower right under ecological research is their underwater panels that are growing oysters at the Presidio National Park. So they weren't sure if they had oysters, and through our research, we've been working with them for 4 years. We discovered that by floating and keeping the oyster panels higher, we've been able to cultivate hundreds of full-size oysters. And this work is informing a new seawall that is coming down the pike in a few years to replace the existing infrastructure along the San Francisco downtown. And so the Digital Craft Lab is something different. It's very much a location within the school. Right now, there has been a space where we can work, both the architectural ecologies labs and students of architecture and interior design. There are robots. It's a place that we have Potterbots, and we'll show some of that work. But what's exciting and coming down that will be happening and being constructed right now is in 2024. You can see the axonometric and the section. Though that's a space that is being built out for the Digital Craft Lab. So we'll have bigger robots and safer spaces for those robots to we'll have really this amazing space for research. And Nagar and our colleague Jason is working to design that and integrate that into the new campus. And in the circles are some of the work that Nagar's students have done in the past. So those are sort of the Digital Craft Lab is definitely a located lab within our school. And the Architecture Ecologies Lab are sites within the Bay that we have research projects, and we have built collaborations with different partners. One of the ways in which this work of biodesign has been supported, we aren't an R1 school and we're an art college, but we're located right in the heart of San Francisco. So it's allowed us to create these very robust relationships. And in this one in particular is Autodesk Research. So Autodesk Research has a technology center. They have 3, one in San Francisco, one in Boston, and one in Toronto. And we are very much involved and have established an academic alliance with Autodesk, which allows us and our students to work very directly within their facilities and under the umbrella of their research and development team to help to explore with their tools and with their this kind of collaboration that just naturally happens because there are other industry residents as well as experts in their research and development department. So they help us inform our work in biodesign, and in turn we give them a window into the kind of research that's happening in academia. Along with that, right next door to our campus in south of Market is University of California, San Francisco. And it's been quite an amazing partnership because we literally are right next door to each other. And so we have been working with Dyke Mullins from Mullins Lab. He is the chair of the Department of Cellular and Molecular Pharmacology. And what that allows us to do, and we'll explain a little bit more, is to work with their graduate students, have a different kind of lab where we have their wet lab there, and then we can bring things over to our lab, the Digital Craft Lab, where it can be, we can mix things into bacteria and things like that that they have created for us into clay, which we'll show you shortly. So what we do, our work involves integrating materials, geometry, and performance in ways of making and creating new efficiencies in architecture and beyond. There are different ways that we can think about this, from design for linearity, design for recyclability, or design for circularity. And this is a simple graphic that I think shows the different ways. What we're used to, particularly in the architecture discipline, is more so about linear economy, where we extract and we make and then we throw away after the end of its life. and there is a recycling economy that is becoming much more part of the dialogue, but we're really interested in pushing the idea of a circular economy. So the linear economy is one which we're all familiar with, which is to take, say, wood to make and use and not really think about how something might be taken apart or reused. We like to eliminate the waste part of this equation. In the circular economy, we would be taking that into consideration, where we take, make, and use. But we also think about reuse. So things that we are specifying in our materials, we think about reusing items, but also how those items might be reused at the end of its life. And by doing that, we can really think about a regenerative kind of system, both architecturally and ecologically. So how that both by the way we build from a regenerative lens, we can also think about how that impacts our natural systems, our natural ecological systems. In the construction industry, we are very conscious of the fact that we contribute 39% of the global carbon emissions. So it's a big percentage. And as educators, we also teach about building operations. Students are learning about how the energy that's needed to heat, cool, and power, and we are teaching about more, how to make energy efficient buildings. In fact, our laws will require that we have net zero buildings very soon. So that's something that is, it's not that everyone can afford to do it, but we have a very good knowledge about how to make energy efficient buildings. What is more of a mystery is the 11%, the building materials and construction. We are less aware about the embodied energy in the materials that we specify when we're building buildings and we're designing buildings. So that's something where this research is looking into, is that how can we challenge the conventions in building components, fabrication, and assembly? And how can we push the boundaries of circular thinking to drive positive change? How can our work actually feel, where we feel like we're active participants in this change? And how can we embark on a transformative journey where technology, creativity, and sustainability converge in construction? We know we can't solve all the problems, but we feel like by tackling these kinds of issues within an academic environment, we also are realizing that our students are very, very much, it's their future and they want to be active participants. So this conversation about biodesign and biodesigning materials for construction is one that is our students are very passionate about, and I'm sure you all are passionate about as well. It's very much a global issue. So more than 80% of the what is interesting and is there is a statistics that more than 80% of environmental impacts of a product or project is determined at the design stage. So we have very early on, we can make a big impact using new tools of understanding embodied carbon and materials, how to calculate that, how to make decisions about that, and then exploring materials itself. And that's not something traditionally we would do in an architectural education program. And so that's our work. Our interest here is to talk about this 11% and how our focus and our interest, the interest between Nagar, Evan, and I, and Dyke Mullins at UCSF, the four of us have become very strong collaborators, and our interest is to continue to push this kind of investigation in terms of materials and how those materials affect construction. And in materials, we imagine us thinking in terms of reuse. How do we use less materials? How do we think of alternative materials that may not be quite available to us right now that we can just specify when we're designing buildings, but how can we start to be creators of alternatives, and how do we use materials better? And in terms of construction, how can we think more innovatively in a more clever way? How can we build more efficiently? And how do we build more sustainably? As well as how do we think about the integration of materials where one material can do more than one thing? So today we're going to speak specifically about alternatives, about one project that is about alternatives, about how that alternative builds more sustainably and builds more integratively. And we want to, particularly with Dan, that will be in this space lecturing after us, we wanted to acknowledge that one of the things that people often ask is, how do you start to do biodesign, like within any kind of program, but for us, particularly within an architecture design program? And about 5 years ago, a very important platform for that investigation has been the Biodesign Challenge. We've participated 5 years, we're participating again this year, and it's allowed us the platform to be supported by their community and to explore things like designing with degradable materials. So instead of thinking about a material lasting for a long time, can we think about designing for the right time, and that at the end of its life, particularly if it's on water, it could degrade and not become part of the microplastic problem? Or in terms of floating architecture, can we think about creating new kinds of living systems that are an infrastructure between nature and infrastructure that can help dissipate waves like marshes do, but now we have no more room for marshes because we've taken them away and we've built cities. But can we build back a constructive marsh that can cultivate oysters, that could be a living habitat for animals and fish, both on top and below, that help protect our seawalls and just help buffer those seawalls as waves come and hit them? I imagine this is an issue that is something that you are dealing with in Chile too, because you have a very big coastline, just like we have a very big coastline in California. So the Biodesign Challenge has been really instrumental in creating a platform that is it's not so much about the competition, but the collaborative nature that competition starts to inspire students. And so the project we're going to talk about today is one that we just presented our team just presented at the Biodesign Challenge in 2023, called Bactera. And this was a collaboration with faculty advisors, Nagar, Evan, Dyke Mullins, and me, and with graduate students, two graduate students from UCSF and 3 architecture students, 2 master's students, and 1 undergraduate student. So we had a team of 5 that worked together for a year on this project called Bactera.
So I'm just going to talk about kind of the context of this project, and also just kind of the generative, what generated it. And so I'm just going to start by looking at these as an example, looking at these two towers. So they're similar in form, and they're at very different scales. But one is a concrete structure, the Marina Tower in Chicago, and the other is a very microscopic view of a sea urchin spine. And they're very similar forms, but what's interesting to think about is that one of them has required a lot of carbon and energy to make it. And the other one is actually requires hardly any energy and is actually sequestering carbon. So this is kind of like the context where we can begin to think about alternatives to materials. So kind of more broadly, animals such as these have used these biological processes to sequester carbon and to build hard shells. And this is in terms of minerals. You look at these mollusks. You also can think about proteins to make hair, and also sugars are used to make hard shells for insects, and cellulose for plants. In our own bodies, we are able to make bones and fingernails. So, and that's kind of this world of biomineralization. And humans, have worked in similar ways using the environment to create shelters. And really, we've kind of built a lot with Earth, more than we've built with our modern materials. And so, for instance, Yaz, which is the city in Iran, which one of our students actually grew up here, has almost the majority of its buildings are built from Earth, and they're still inhabited today. And it's really only in the last 300 years, when you think about kind of the embedded cultural knowledge and traditions, that we've kind of deviated and began to look at use reinforced concrete for the majority of our buildings. And concrete it's really one of the most used materials. I think water is the only material that's more used than concrete. So we really have to begin to be conscious of the kind of energy involved in making this. So for instance, concrete takes raw materials, which is actually limestone. It's heated up to 1,500 degrees. So all that carbon is just thrown into the atmosphere. And then it's mixed, it's transported. You have about 50 to 100 years maybe of a building out of concrete, and then it's demolished, and most of that gets diverted to a landfill. Whereas so just thinking about kind of the past of Earth buildings, and then thinking about kind of the future of what's going to happen with all this CO2 and what we can see happening, all the CO2 getting put into the environment and affecting the climate. We really need to also think about where we are in the present. And right now we're kind of at a very interesting point where the convergence of computational design, additive manufacturing, and kind of material engineering. We have a lot of capabilities now that we can begin to combine and synthesize. And that's, I think, where biodesign is kind of the forum where that can happen. So thinking about the microscopic world, I mean, can that provide an alternative to this kind of massive footprint of concrete buildings? So looking again at a sea urchin, the shells, we begin to see a tremendous complexity at various scales, and how through just biological processes, they're beginning to create differentiation, identify different structural requirements for the animal, for the shelter, and how it can actually just grow and begin to expand. So just on a very simple level, can we partner with these bacteria to produce building materials? So kind of the most elemental creature that is capable of producing these kind of calcium carbonate shells is a bacteria. And so we began with UCSF looking at bacillus, which is it's a bacteria that's in kimchi, it's in our beer, it's in our food, it's a part of our microbes, it's in our oceans. It's very safe, and it is capable of creating biofilms, creating calcium carbonates. So we began to look at this material, or this bacteria, and think of, can we begin to mix it into a building material, and can we leverage the fact that these calcium crystals are being made, as opposed to concrete, where they're being, they're being made, but after all this energy. So at UCSF, they began to mix this bacteria medium for us, and we began to experiment in putting it into clay and extruding it. This is a Potter bot. It's basically an extruder for clay, and we began to experiment with various forms and finding a way to get this medium to be in extrudable form. So this required a bunch of tests. We began just with the actual material, looking at issues of shrinking, cracking, then moving on to kind of more specific tests about how we can actually extrude it, what forms make sense. You can see the bacterial medium that Claire's holding there in the middle. That was given to us by UCSF. We walked it over, and they kind of grew it up to the level where the bacteria have sort of peaked in population, and we would mix that into the material and have it harden kind of at the peak time. So this really couldn't have been done without working with scientists and students who understood this. The next test, you could see the different forms. There's cracking and some of those failures, but eventually we began to sort of evolve a kind of working methodology with the material. And the net result is that we were able to do some structural tests showing that compared to the raw unfired clay, the bacteria actually provided about 3 or 4 times the strength, and then mixing it with the sea urchin shells gave it even more strength. So just using raw sea urchin shells embedded in the material. And another great thing is that just as UCSF gave us this material, we actually brought the material back from our digital craft lab where it was made, and they were able to look at it through their electron microscopy and see some of this calcium crystal formation within the material. So thinking, conceptually again about what's possible with these robots, with these extrusions, we began to think more extensively about the geometries that could facilitate kind of a robot with a certain extension, and thinking about extrusion itself. These are some tests at Autodesk Technology Center, where we actually do have a robot that has this ability to extrude. And what you're seeing on the left is the ability to print out of plane. So just as a seashell might kind of wrap around itself, that's kind of a capability that the PotterBot doesn't have. So it's just the next evolution of kind of digital fabrication, and then what geometries can come out of that. So that led us to speculate about how we can grow this idea of living buildings, about what forms can they take. And so then, architecture design begins to become very, it begins to get spurred by this kind of interaction, this back and forth. And Dyke Mullins had just a great quote that sort of captivated us, where he just said, "Biological systems arise, they self-assemble, they do their job, at the end of their life, they die in a graceful way and their carbon goes back into the pool. So that really captured this idea of the circular economy, the circular fabrication. And I think that's just a small step of where the work is kind of just touched on, I think, and has a lot of promise in the future.
So one of the, because of the Biodesign Challenge, because of our collaborations, and because of our interest in engagement, we were able, leading up to the Biodesign Challenge in June, have conversations, excuse me, that was our cat, in the architecture division, where our students presented their in-process work and got feedback. We had a panel discussion where the greater college got a window into the biodesign work and biomaterial investigation. We took that work later to Autodesk Technology Center, where industry leaders and residents got to see the presentation at a later stage, give input and ideas there. And then lastly, we went to UCSF and presented the work in a science community with different scientists from their perspective. So it was just very interesting for our student team to see the interest from different perspectives, which is really how I feel that we feel like this work starts to gain momentum and depth. We also took the work into the public realm to engage the public. We were part of an after dark Thursday night event about a multi-species design, and where we set up, UCSF brought one of their very expensive microscopes, and we had our experiments, and people could, our team could talk to the public and then show the different bacterias in the microscope. And so we were very excited. This last year, our team did very well. It was in person. It had been many years that it was online. To be in person in New York, to meet the greater community again, to be part of that, feel everybody's energy just in itself was great. But it was also very exciting that our team won the Outstanding Science Award. And from that, this year, we are building off that. We decided our new constructed ecologies would just build from that work. They had kind of began to set the groundwork for biomineralized clay. And now that work is evolving through 19 students that will be presenting their work very shortly. And one of these projects will be chosen to go on to continue to develop until June. And on the left, we just went and visited the UCSF, the lab there. And the last slide, we just wanted to share some of our learning outcomes that we feel right now, that some of the things that we feel like are very important is the converging of multiple scales of understanding. So knowing things at a broad scale of maybe how its impact on the globe, as well as in urban environments, as well as living, but down to the microscopic living. So being able to have tools to understand it at all scales, extending research beyond academic silos. This work is not possible, and I'm sure all of you are well aware of that, if we only work within our own discipline. It's just not possible to do. And the creative value of informed and naive ideas, which might be perspectives of architecture in science, but scientists in architecture, and engaging with the wider public, like Biodesign Challenge. And for us, contributing to open source knowledge. So creating free access to the information that we have developed within our college, and this very pivotal moment of how we can adapt new technologies like this 5-axis robot to really begin to understand shell building. So this is our group, the Architecture Ecologies Lab on the left, the Digital Craft Lab on the right. And Our emails are here. If you have any questions about our work, we'd be happy to answer questions. We are already wonderfully having great conversations with your faculty about how we can collaborate from Santiago to San Francisco. But please reach out to us. And if you come to California, please come and visit us. We'd love to, especially next year, we'll have a really amazing new campus to share with you. So thank you. So I think we have a few minutes. We're happy to take questions if you have any questions for us. Although we can't hear.
We can't hear. We see the applause. So, but so if you have a
Margaret,
question.
Evan?
Yes.
Here I am. Well, thank you very much. First of all, this is very interesting. And si alguien tiene preguntas, tengo acá el microphone.
Hi, Margaret and Evan. It's Christina.
Hi.
Thank you so much. A fantastic talk. Just a quick question about I think it was PSI between the clay without the bacteria and then the 2 additions post. Was the clay fired at all, or is it 400 PSI with raw clay when you did the test?
Yeah, we were looking like, thinking about earth architecture. We were really trying to avoid like any energy. So really trying to get to like what can you do without using any extended energy. So we didn't even test fired clay because it wasn't really what we were trying to investigate.
Fantastic.
So
you got
clay
the
with
results.
Water.
Clay with
so,
water, dried. Yeah.
And then clay with bacteria.
Yeah.
And then clay with used sea urchins is a problem right now in the Pacific coast, northern Pacific coast, because of the die-off of the starfish. And so they're really starving and they're multiplying, they're eating our kelp. And so there's a lot of scientists that are working on researching sea urchins. And so we are collaborating with them. They send us their urchin shells after their research from San Diego. And then we clean them from all their tissues, and then we pulverize them. So we made them
basically used as an aggregate for the material to see if it was stronger. And it was slightly stronger just using that raw animal-made material.
But I'm sure you can, the idea is, can we start to supplement earth materials, clays in different parts of the world with very simple bacteria that could be resourced? So that's kind of the investigation for this year, is how viable that is. Because right now what's happening with new when you're making earth architecture right now, either you're using concrete as it's integrated into, like, it might be earth, but then the concrete is really taking all the loads, or they're mixing concrete into the earth. And either way, it becomes concrete. So we're trying to see if we can do it with just bacteria, not even adding a little bit of concrete. We're trying to see how strong we can get this material without using any concrete at all. It might not be possible, but that's where we're going.
Yeah, just a quick question going off of that. Did the integration of the sea urchin shell kind of change the pore size as far as the before and after?
The what size?
The pore size, the pore size within, like, when you all were looking at the electron microscopy and such.
Oh, interesting.
No. Yeah, I don't know exactly.
That's a good question. You mean, is the material more porous in a way?
That's right, because then
I would say at that scale, you're probably going to see just like chunks of sea urchin and then the rest of the clay medium and the bacteria. So,
but that's a good question, because we're having them do more microscopy from new batches, and we can ask that, because I'm not sure. But that's what's been pretty exciting, to see it at that scale, to be able to go back into that kind of microscope. I mean, it was a thing that inspired us from the beginning when the scientists started. We weren't the one that really knew how sea urchins looked at a very microscopic level. It was the graduate students at UCSF that brought those images. And that's what inspires, like, oh my God, if you look at this tower and you look at the, the sea urchin, they're almost the same. And that's, it was those kinds of unexpected kind of convergences that you start to inform each other in ways that are, we would never do on our own. It's very fun.
Kind of another scientific kind of inspiration, which biodesign actually was able to connect us to about 2 or 3 years ago, is a professor in China named Dr. Achel, who has looked at the kind of the cracking in concrete and looked at the kind of porosity of concrete, and was looking at this very simple bacterias, which can begin to sequester, like, as water infiltrates these bacterial spores come alive and
that are dormant.
That are dormant within the material. He was studying concrete, but they're able to precipitate calcium and close those gaps. So those microscopic pores are able to be sort of closed by the bacteria getting reactivated. And so that's another area of thinking about this material, is that it could actually self-heal. It could come back to life, and with certain nutrients sprayed on the material, it could begin to sort of create less porosity and become more weather resistant.
One of the other things too is with the 3D printing, this is not quite your question, but it just sort of triggered something that we didn't mention, that with 3D printing and curves, you can use less material. So you can get much higher strength with using less materials with curves. And so that's another thing we're exploring. But thank you. Thank you, because we'll ask with this next iteration of images to ask them to look at that more specifically.
Hi, can you hear me?
Yeah.
Yes.
Okay, hi. So I'm from Davis. I am an engineer, and I work with a civil engineering professor. He's actually developing earthen structures, and he's found so much resistance from the construction industry to use these materials. And I was wondering if you had the same experience, because they just don't want to change from concrete. And so if we want to make an impact in basically in the world, then we need to convince some of these very traditionalist concrete people to just adopt these materials. And one of the things that he was showing was also the ability for some of these earthen materials to have much better fire resilience.
Oh,
so
yes.
Yes. You had the same,
Yes.
Perception.
Yes.
Yeah.
Very, very important. Because you've probably heard about all our fires, and it's now happening around the world. So it's not just in California and the West Coast with our forests. It's a huge problem. And I think that's one area where people will perk up, because you can you can still have wood on the interior, but you could protect it with earthen on the exterior. And earth structures are fire resistant. So there's a tremendous amount of potential. And historically in California, we have used adobe. So we're not as much of an earthen architect, where there's not as much obvious earthen architecture, say in the Southwest, where in Santa Fe and places like that, they still use a lot of earthen architecture. But historically we have. And so we're kind of revisiting. I feel like maybe not in the industry yet, but definitely in academia is where we can start that, because we understand codes, we understand the constraints. Part of the reasons you have to use concrete is that concrete is known. We know it will take the kind of gravity loads and support buildings in the way, but
it's true. We have written in and embedded these materials, these very environmentally destructive materials, into our code and made them easier to use, even almost like the default material, right? So I think one of the things we learned from earthen architecture and looking at these cities all over the world that have used earth to build is that there is a lot of embedded cultural knowledge. There's a lot of understanding of maintenance, that we don't really have over there. There's celebrations every year where they begin to like add to the building, maintain the building. So it's very much not like our industrial kind of make the building last for 10 years so we can avoid liability or just build it into the code. We have to really almost transform the underlying culture surrounding the building in order to kind of, I think, make a change. So just visualizing some of these possibilities, like with some of these speculative views of what this architecture could be, are sort of begin to move that very difficult
dial. And also events like this that you all have put together and learning about the work that's already happening. I really feel like the way things are going to move is by all of us becoming more knowledgeable about each other, helping each other with information we learning from each other so that collectively we can start to make a move together and showcasing. So we're a big believer in being able to have proof of concept. There's nothing like proof of concept, nothing like making prototypes, testing prototypes, letting them be in the weather, letting them perform to see what's possible. It's the only way it's going to happen. And I really feel like collectively we have to do that together. So,
and ultimately that's the technology that is going to begin to justify and give grounding to just like concrete has strength tests, we'll have the same sort of standards beginning to emerge for these newer or older
but we'd love to learn about the project you're talking about, your colleague that's doing that. So maybe
I actually going to connect you to him because
it'll be wonderful.
As a civil engineer, his name is Michele Barbato. He's having so much resistance against any of this, and he's a structural engineer by training, and so he's just like really frustrated and he wants to do all of this, and so I actually don't know that he's aware of your work, so that will be a very good connection.
Yeah, I feel like we can all support each other when we get frustrated, absolutely. But also use our leverage because we all have different kinds of. It's really like it's a paradigm shift for all of us. I mean, we're also we're used to specifying. We're used to, in the United States, you don't want to get sued if a material degrades or it's usually like no degradation. But can we flip this? So we have to flip our mindset as we are exploring new paradigms of building materials.
I think we would be very interested to see, for example, your fire resilience of your structures if you haven't tested that yet.
Mm-hmm. We haven't yet, but that would be really good. Yeah. And the state of California would be very interested. There's a lot of interest now in rammed earth kinds of materials for that reason because of its fire resistant capability.
Perfect. So we'll make the connection. Thank you.
Yes, thank you.
The discussion.
Hi, hello. I want to follow up on the spirit of that question. So I want to ask, because I'm not an expert in the technologies themselves, I'm an art educator. So I wanted to ask, how scalable are these technologies in the sense of thinking about developing literacies, sort of material literacies that I think might be necessary for the future, so that we all enter these discussions. Are these kinds of technologies that we could then take to, because I'm seeing that sort of clay 3D printer that we played a lot in maker spaces when I was studying in the US. So I'm thinking, like, could we take that to a more general population so that we could start discussing these things beyond academia and the industries, which are harder to move, right? Because we have more harder beats to move. What do you think of that?
Yeah, well, I mean, what's great about 3D printing itself is that, especially if we think about using the local earth material and just 3D printing with it, is and I should just say that there is a huge amount of research now in terms of large scale 3D printing. So we've gone from these little plastic printers, that can do this, something like that, to like these things that can print buildings. And we are printing buildings. The majority of them are using concrete. unfortunately, but I think the technology itself is really advanced or just progressing. And so I think really thinking about one material, using that material, I mean, it is seems very high tech, but in another sense, it's very low tech. So it kind of, it's a single print, single material, you know, that has advantages in deconstruction, but it also has advantages, I think, in assemblies. So,
but it also could be handmade. So we're also
Yeah.
thinking exactly what you're saying. How does a greater public how does this become accessible? Which is the reason why we worked with the UCSF. We're all on the same wavelength in terms of what is a bacteria that is very safe and easy to get anywhere in the world. And then how do you begin to communicate a kind of construction method that could be hand by hand bricks or coiling, like when you do ceramic pots, you can hand coil, or you can start to now 3D print. So there's just different scales of technologies depending on what you have available, but the material itself is something that we're exploring at any kind of level of sophistication. How can we communicate the making of this material? And we are not alone. This is not new. People have been doing mineralized clays and things like that. There's been a lot of work in it, especially in engineering. But I think in architecture, in terms of 3D printing, we see a lot of potential for minimizing waste and also thinking in terms of components. So we might not be thinking of 3D. You could print a whole building, but you could also create components that start to be like a new kind of brick.
And if those things can grow together, you know, if the bacteria itself can begin to fuse two separate, just like it fuses two layers of printed material, could it fuse two components? I mean, that's another area that I think could be very, very interesting to look at.
Yes, absolutely. Thank you very much. That's very interesting as well. I don't know.
Hi, so I'm a grad student researching biomaterials.
Oh, excellent.
Especially things reinforced with natural fibers. And one of the biggest challenges I'm having is that natural fibers are naturally very varied in size, composition, resistance, and a lot or most of the methods to homologize them involves reducing their strength. And I think this has to do with the code and getting industry on board. Is there a point where we should just accept that biomaterials are going to be imperfect, and how do we push back against a code or an engineering system that wants to have 100% predictivity in their materials and accept that there's going to be some variance, some unpredictability, but just design around that constraint and that it will probably be enough?
I mean, there is work that we know is happening both ways. I think it's a gradient. I think exactly what you describe is one aspect of how to really think about working with biomaterials, which is so different than we're used to thinking in terms of materials we specify, which is longevity, which is stable, that does not change. In fact, that would be the goal. It does not change. We're talking about how living systems can actually change, make something adapt, and make something adapt in terms of maybe healing, and just like our bodies do. But there are people too that are in the industry using things like mycelium and substituting a filler that might be used for creating panels with mycelium, and then you can bake that mycelium. It's dead, but you're switching out a petroleum-based product with a natural base. And that's being done, and that's pretty exciting. And then that's not challenging people because it's stable once it's inside these existing panels. But then, you know, I think you just have to think where there's different ways and different places to land. But the idea of these kinds of natural fibers are, especially if you're looking at like reinforced kind of materials, like FRP or fiber reinforced polymers. The idea of using natural materials like hemp and linens and things like that are not uncommon. It's really the resin part that is difficult, because at least we found that part difficult. Like, how do you can get a resin that has some petroleum, there's some bio mixed into it, but it's not 100% as far as we know.
But I think, I mean, we do build with a natural material here. With California, we have wood, and wood is a variety of qualities, and
it's not stable.
It's not stable, it's warps, it's you make it work with the redundancy of structure, and you factor, and that's been factored into a code. So I don't think it's sort of insurmountable. I just think it's about kind of reframing and maybe quantifying the kind of levels of redundancy, and kind of basically getting it up to a standard where somebody can say, oh, okay, well, you're 20 times stronger than the worst case scenario, so you can put in this many fibers, and so I don't think
what is the fiber you're exploring?
Agave fibers from
Oh yes.
Yeah, waste from the tequila and mezcal industry.
Oh, yeah. So I think those are really strong, just like bamboo, strands are strong. So.
And totally worthy of your investigation, because, reinforced concrete is only 300 years old, which is kind of crazy when you think about earth and architecture. And it's through that investigation that we realized that there is a really wonderful relationship between steel and concrete, the way they move together. And so you may find the same kind of discovery, with another material, that they work really well together, that there's a symbiotic relationship that can happen with one material that's a fiber that takes tension really well, and other that's very good in compression.
Yeah.
But we might not know what that combination is yet, but I hope that, I look forward to seeing your research.
Thank you so much.
Okay, so
Great.
Evan, Margaret, once again, thank you very much. I think we could keep this conversation going for a long time, right? So
well, you guys are, so I'm really happy.
We'll
chime in on some of your other conversations, and
at a later time.
We look forward to learning more about what you all are doing too.
Mm-hmm.
And please come and visit us in California. Anytime you're here, just like when we met you, we'd be happy to show you around.
Yes, well, thank you very much. We need to be moving to the next part of our workshop. So Evan, Margaret, once again, thank you very much. And
thank
you, everyone.
Yeah.
Bye. Take care.
Hello, Dan, if you're there. We're having a break right now, and we'll start again at 2 with your talk in 40 minutes.
Great. I'm here. Just call out my name and I'll turn on my video. Do you hear me?
Yes, we can hear you.
Great. Okay, I'll be here. See you soon.
Perfect. Thank you very much. Hola, Dan, are you there?
Hi, I'm here.
Okay, thank you very much. Bueno, igual que antes, hay traducción en vivo. Si necesitan un auricular, pueden solicitarlo en la parte de atrás. We will be translating. Dan, thank you very much for joining us. We're here for the second part of today's seminar on biodesign, architecture, and bioethics. Dan is the founder and former director of the Biodesign Challenge, this initiative that aims to grow collaboration around biodesign globally. I think us being here is already a big part of that endeavor, and our school has been participating in the last 2 years, and we have had a successful participation in both years, partly thanks to Christina and her team and all the collaborations that we've been holding on the last few years, and also thanks to Natalie Silva and Enzo Anciani and the Design School for enabling a biodesign workshop to go on every year. So Dan, we'll leave you now for your talk. You can share your screen. Thank you very much.
Hi all. I'm assuming you can see this.
Yes, we can.
Okay, great. Okay, so allow me to think out loud with you all for this next 45 minutes to an hour. And before I do, I just want to thank Christina. I want to thank Ricardo, Margaret, and Evan who spoke earlier this afternoon for you all. Have been huge supporters of Biodesign Challenge and really leaders in the community, and it was fantastic to see their talk. And of course, I want to thank UDD for inviting me to be here, for being in BDC for the last 2 years. I got to get out there, so hopefully soon. I guess when winter comes, I'll be on my way. All right, so let me tell you a little bit about myself. So many years ago, 15 years ago, I co-founded an organization called GenSpace. GenSpace was the first community biology lab. It was built on the idea that the tools of biotechnology should be available to anyone, not just biologists, not just biotechnologists, but people from all walks of life. I was a journalist at the time. I was writing about biotechnology, but I had never taken a class in biotechnology in university or biology in university. And here I was writing about it for Nature, Biotechnology, Nature Medicine, Scientific American, and I was slowly falling in love with biotechnology. At a certain point, I wanted to try it, but for someone who was well into their career, that wasn't an option 15 years ago. And so we created that option. We created GenSpace, which is the world's first community biology lab. And very quickly, the idea spread from there. And so these spaces, which basically are like, I would consider them community centers, but instead of being built around the pool or the gym or the auditorium, they're built around the biology lab. Very quickly after we established that model, it spread across the world. So here's a map from the DIYbio.org showing the various labs around the world, and then the various groups that are doing this type of activity. From there, it became very clear to me that when you open up these spaces, people with different perspectives are going to create different projects that don't look anything like what you would find in a traditional biotechnology lab or a traditional biology lab. The solutions that they're looking for, the problems that they're addressing, are very much tied to what they're experiencing in their life. And so what you get is a plethora of new ideas, new applications that just wouldn't have happened had they not gone into this space outside of the traditional spheres. One of the groups that showed up very early on were designers, and it became very clear that designers and artists, when they work hand in hand with biologists, start to create projects that are much both deeper technically and also broader in the sense of their applications. And so 8 years ago, in 2015, 2016, I created the first Biodesign Challenge. And the Biodesign Challenge was a way for us to get scientists, designers, artists all working together, but through students, usually university students, but these days we also work with high schools. And essentially we ask the students to be, I don't want to call them the guinea pigs, but they're the creators. And they work under the advice and the mentorship of both scientists and designers, and sort of have to take in those two very different perspectives and inculcate them into individual projects. So on the campuses around the world, every year, students are doing that, and it's built into usually design classrooms or biology classrooms. The students will mid-semester break into teams. They'll start developing projects to address some issue out in the world or identify some issue out in the world. And then they'll present their projects on campus as a sort of a round one of our competition. So they'll present them to their instructors, to the mentors, to the deans on campus. And then each school will choose one team to represent the school at our grand summit, which takes place at MoMA each year, MoMA, Museum of Modern Art in New York City. And all the students with their projects will get on stage, and they'll present their ideas before judges that run the gamut from both biotechnology to design to museum curation to social science to ethics, you name it. We have 50 judges, and they come from all walks, and is a great challenge every year, but they pick one team to win the glass microbe, which is what you're looking at right now, and then several other prizes. Biodesign Challenge started in 9 schools, but it's grown each year. And so this is now dated. So far, we've had 247 finalist teams, but you'll see we've been in over 20 countries around the world. And this is just a short list of them. This is actually dated now because it doesn't encompass 2022. So yeah, it's grown internationally, and the impacts have been grand. We've seen students take their ideas and put them in galleries and museums around the world, everywhere from the V&A in the UK to the MIT Museum. And then we've seen startups emerge out of Biodesign Challenge. So last I did the calculation, we were roughly around $30 million in funds raised for the ideas that have come out of the Biodesign Challenge. 2 days ago, another $5 million was raised by a group that had made a leather-like material using shrimp waste. So now I guess that puts us at 35 million. And I'd like to think that the ideas have been transformative, both for how we think as designers, how we think as biologists, but hopefully how we address sustainability solutions. Okay, so the point of this talk is really to talk about codes of ethics or principles by which to do our work. And so what you're looking at is essentially the back of the envelope diagram that I drew of biodesign before there was biodesign. And you see that it's basically what we were trying to create is, if you think of the circle as a round table, that the biologists and the ecologists and the ethicists and the policymakers and the designers and the artists were all sitting around a table, basically negotiating what should come out of biotechnology. Innovation based on a set of principles is what I wrote. And then time passed. And in 2021, I wrote an article in Issues in Science and Technology, which was an attempt to define what biodesign is. And the only way you can really create a set of principles is if you know who's in the room, who's sitting around that table. And I contradicted myself. I basically went back on those sets of principles, and I wrote, and I base it on synthetic biology. And I'll just read this to you very quickly. In 2009, Nature Biotech asked a group of synthetic biologists to define synthetic biology. None of the scientists could agree on a definition, yet today the synthetic biology market, a field evidently without a widely accepted understanding of itself, is worth 9.5 billion. When Nature Biotech posed its question, I was a reporter covering the emerging discipline. I soon realized that definitions are less important than the groups of people who gather around and advance a particular set of ideas. So what then is biodesign? Today, I would say it's a big tent where everyone who self-identifies as a biodesigner can hang out. Of course, before I founded Biodesign Challenge, I probably would have said that it's a design practice that incorporates biotechnology, or one that uses design to critique the biotech industry. So years after I put down that little chart, I flip-flopped and started to think, well, maybe it's just biodesigners who sits in the room. And so folks like Margaret and Christina and Evan, they're the ones that make biodesign. Well, I flip-flopped again. So I want to go back to thinking about what does a code of ethics look like for biodesign. And the reason why that's really important to me is because I think that we are at a point where scientists and designers need to come together and start to understand what is our aspirations, what are our goals. So I went back into my memory and started to think about when was the last time I worked on code. And this is basically it. So I showed you that first picture of GenSpace. Well, as different labs around the world were starting to form, they faced a problem. Number one, the media and policymakers saw them as a threat. Here are a bunch of amateurs working with biology. Aren't they going to make a mess? Aren't they going to use it for applications that are dangerous or unsavory? And so we spent a lot of our first years when we created the do-it-yourself biology, which eventually became community biology practice. We faced a lot of criticism even before we got started. And so Jason Bobe, who was one of the founders of DIY Bio, basically put together what we called at the time a Continental Congress, where he brought leaders together from various different labs to establish what it is we are, what it is we do, and why we do it. And so there's a lot of text in this presentation, so bear with me. So he basically outlined for us what are the purposes of codes, and here's how he defines it. The development and adoption of a code may help foster, hold on, I'm off screen, norms and establish minimal ethical standards. As new practitioners join the community, a code may function to clarify certain individual and collective responsibilities and establish a common set of considerations for reflection. The coding process itself can serve to raise awareness about important issues, stimulate discussions, and achieve education goals. And what he outlined are 3 types of ways of writing codes. So one might be aspirational, which is basically the ideals that practitioners should hold. Now, I would argue that there's 2 types of aspirations, but we'll get to that in the talk. Next would be educational. So these are guidelines for how one should behave within this organized set of groups. And then the third one are codes about enforceability or enforceable, codes about compliance. So you sort of do's and do nots related to safety or different sets of ethics. I think the biggest thing from this list from what he described was this last bit, which I have circled. The process of coding may be as beneficial for norm development than the code itself. And insight captured by the phrase, a code is nothing, coding is everything. And the argument there is that, well, the codes are just words on paper, but the actual act of establishing a code of ethics is actually the work, and that's what's transformative. We shall see. So when I worked with Jason, this group of different folks from around the United States or the North America came together. There was a second group that also came together in Europe, and we basically came up with our codes of ethics. And very quickly, you'll see that they, by I guess osmosis or just as sort of the zeitgeist of the moment, the codes very much paralleled each other. You know, they were what was very important was open access, giving everyone access to the tools of biotechnology. 2, transparency, giving people access to the knowledge of biotechnology and how to do things. Education, informing the public about biotech and its possibilities. Safety, of course. Respect for the environment. So, you know, what it is, some of the purposes of biotechnology or what we're doing as community biologists. Peaceful purposes, which I would say is, you know, not making bioweapons. And then for us, very important was talking about tinkering. You'll see when we look at the European version of this, very, very similar. I will say that they were a little more, I would say, sensitive to modesty and accountability. And I think there's something to be said that we were writing our codes in Silicon Valley while they were writing them in the UK. But again, what this was able to do was basically have us identify that we were actually working towards the same purposes. And instead of us working individually in our individual labs and hoping that the others were doing the same, suddenly we shared this code where we knew the other labs were doing the same. Interestingly, you know, this was done in 2011. Interestingly, 10 years later, roughly 2019, a same exercise was done at MIT, and they did it differently. By the way, before I go on to what they wrote, we had an artist there who was basically visualizing all of the conversations that were going on to help negotiate these codes. And so this is what it looked like. So in 2019, a group in MIT did the same exercises, and they decided that they would do it a little bit differently. They would basically, instead of having commandments, they would have a set of questions. And I would argue that this was actually less successful because it's very hard to come up with similar sets of ethics when all you're faced with are questions. There's no way to sign on or not sign on to a project like to a code like this. And I'll show you. So several years later in 2020, about a year ago, we went back to these code makers. So both Jason and Alex Perlman, who's a bioethicist now at Ginkgo Bioworks, who had led these, who had moderated these groups. And we asked them, what were you doing with these codes of ethics? What were you trying to achieve? So here's how Jason answers, and then I'll show you how Alex answers. So Jason says, my motivation for DIY biocodes was to express the values of a nascent community that I and many others believed held great promise for society. Others were more skeptical. Skepticism about any idea in general is generally expected, but at the time, the public conversation around this new community fixated on scenarios in inevitable doom ushered by a legion of basement Frankensteins. That's very true. This seemed like an important moment for the community to reflect on what we stood for and to share that with the world. At the time, we were saying that biology is the most important discipline in the 20th century, and some of the most important things will flow from access to biotech tools and know-how. And you, the general audience, could be part of it. We wanted to create resources like community labs to spur education and innovation on a local level. We dreamed of having an outpost in every neighborhood, but we hadn't really paused to ask whether anyone might want us to be a neighbor. And so in the end, we asked, what are we all about anyway? So the code, in a sense, helped firm an identity among the DIY labs. Now, 10 years later, after that identity was formed, it was easy to revisit the code and reframe them. So this is what Alex says. The most surprising thing for me was that the document we developed at the Global Community Bio Summit in 2019 didn't resemble a code at all. Instead, the ethics document is a choose-your-own-adventure style activity. It prompts the user to think critically about the ways they can produce ethical work. It's interactive and much more personal than the average code of ethics, which is usually stagnant and boring. This also means that two groups using the ethics document to make their own codes might end up with radically different results. But that's what makes it special and what I think makes it work for community biology. So you see one version of a code and a very different version of a code. One code by which for people to come together and share a set of beliefs, and a code that's far more flexible and allows for a varying set of beliefs. If there's one slide you're going to take away from this talk, I know it's this one. And this is about codes as in the sense of what they can do, what they can't do, what you should think about when you create them. I highly recommend reading this. This came out in March. And I'm just going to highlight a couple of the different sort of tenets of this. There are 13, but I'll only talk about 4. So number 1, codes are fragile. And that's really important to think about. Well, what can a code do and what can't it do? If there's no specificity in a code, it's not going to be helpful in bringing people together. If there's no way to enforce a code, it might be considered toothless. And so how do you actually bring people together around a code? If you can't, then the code is as useful as the paper on which it sits. At the same time, number 2, codes can wield great amounts of power. Codes have the potential to shape social behavior in ways that basically go towards ethical principles. And so while they can't be easy to enforce necessarily, they do bring people together. And then number 3, that the other one I wanted to talk about is that codes are, this is number 4, codes are inseparable from wider socio-technological or technical systems and contexts. Remember, like when you're building a code, the code exists in the context in which you build it. So when we first started the DIY bio movement, we were dealing with a hostile policy community, a hostile biosecurity community. And so a lot of what we were thinking about was in response to that. At the same time, we were still figuring out what we were about. And so I think, given that context, we created one specific set of codes. When those risks have vanished, you got a totally different set of codes coming from the DIY biologists, community biologists 10 years later. I would argue that number 10 is also really important here. Focus on collective responsibility. Often when you look at codes, they're sort of do's and don'ts for the individual, which is fine, but it's much more powerful when it's do's and don'ts for the community writ large. And so a code that describes in a few sentences or in a few commandments the aspirations of the group, that allows people to join and not join depending on what it is those codes say. Similarly, who's in the room matters a lot. Sometimes, you can't have everyone in the community in that room. How do you choose your representatives? There are a lot of questions that have to be asked that in effect change how the code gets written. And so if the biodesign community in fact does need a code, these are really important considerations before we even get started. I'm going to show you a couple of examples that I've been looking at, again from the biology community, because that's my origins. There's a lot. You can look at model rocket clubs have these types of codes. The scuba community has these types of codes. If you start looking, you'll find them everywhere, and they're quite effective. So here's the synthetic biology yeast project. I mentioned this one because they just literally finished synthesizing 50% of the yeast genome. This was 2 weeks ago it was published. And they've managed to create a synthetic chromosome that would go into the yeast, which they could code to their liking. Really impressive project. But I just want to show you how they broke it down. So you have sort of 4 rules for societal benefits, and they're very general. We will conduct and promote our work for the benefit of humankind. Well, that's pretty broad. How would you define that? Which element of humankind? Who gets left in? Who gets left out? We will participate with the project's efforts to engage with the public and be transparent and open about our work. So super important, but at the same time, we'll respect intellectual property. So there are lots of tensions and balances happening in this particular document that get encoded in the actual words. You'll see a huge percent of this document is about safety, what we will and won't do, what our safety practices are, how we distribute those safety practices. And then the third section here is governance. Super interesting, very effective. Here's a picture of that artificial yeast, by the way. This was published in Nature. Here's another example. This is the synthetic biology community. So synthetic biology, I would say, is sort of the father of the DIY bio movement or the community biology movement. But the DIY biology movement created its code of ethics a full 10 years before the synthetic biologists came to some consensus at all. And they've made it incredibly, incredibly succinct, right? They have 6 tenets. Seek to create products and processes that benefit people, society, and the environment. Wildly interpretable. Maybe this might not be useful code, right? Because that is too general. Consider and weigh the benefits of research against potential harms. Incorporate equity and justice. Seek to openly distribute the results of your research and development. Protect the rights of individuals associated with engineering biology. Support open communication between researchers and the stakeholders who might be affected by the research. six tenets. Now, I don't know if I can say this is successful or not. Partly what I think this code is trying to do is to get the researchers to sit down while they're doing the research or before they publish the research to decide what they need to consider in the broadest of senses. And it could be debatable whether they meet these types of ideals, depending on who's reading the ethics, who's reading the page. All right. So going back to my original statement about the biodesign community, part of what you have to do when you create a code of ethics is establish what it is you do as a community, sort of the boundaries of what it is you do. And so Christina Cogdell in the audience probably won't like this slide. It's extremely, extremely basic, but I think it's a little bit helpful in understanding the origins of biodesign from my perspective. Sorry?
Es levantarte cada mañana y estar emocionado. Mis estándares son los sueños de las personas. Si vosotros os juntáis conmigo y mis colegas cada día.
Okay. So yes, I'm sorry, I'm just hearing some feedback. So going back, so yeah, so here's a simple genealogy. Biodesign's origins start in one, critical design and bioart, synthetic biology, which I've already discussed, and then the sustainability and environmental movement. And through them, they sort of filter down through speculative design, DIY biology, which I described, and of course, biomaterials research. All of these are coming together in biodesign. And I think there's something really important to be said that critical design bioart is part of its origins. Because in a sense, what that means is there's a safety or some sort of check built into the foundations of biodesign. Critical design often will take a look at the technology and start to ask questions about it, uncomfortable questions about what's possible, about what it says about our ethics. Similarly with bioart. So really baked into biodesigner is a criticality that I think perhaps other research areas doesn't have. And you see it in the way that we run Biodesign Challenge. So I often show this this little chart to our students and our professors, and you'll see that the types of projects that students produce run on this kind of this graph. So on one axis you have the speculative and the actual. So right, students are free to create projects in the lab that are usable now, or prototypes that are usable now, but they're also welcome to speculate about where the science might be leading. And so you get these projects that feel a little bit like science fiction, but if there's enough scientific evidence today of what might be possible 10 years from now, you start to enter into terrain that's quite interesting and leads to questions that need to be asked. Similarly, we have a second axis here, which is on the problem finding and problem solving axis. And so some projects might really look into what might go wrong. What are some of the ethical issues when you develop a technology? Are there ethical issues embedded in a technology? Sometimes there is. Certainly, let's think about AI as a good example in our current day. Similarly, there are lots of applications for technology, and presumably, hopefully most, which solve real-world problems. What are the real-world problems that we want to have solved? And so if you can fit your project, or usually we can fit a student project on this graph. Sometimes they'll sit right in the middle, which I think tend to be the most interesting projects. And you wouldn't see that in other fields. So if you were looking at a bioengineering class, you would never see these kind of problem finding projects. They would be very skeptical of the long-term speculative projects. This gives us a lot of room to explore. So about a year ago, so I also edited an online magazine called Biodesigned. You can check it out, biodesign.org. We haven't published in a while, but there's a lot of good evergreen material in there. So a year ago, we did an issue on codes. Excuse me. And so we started to think about codes. I think one of the codes worth considering is the code by which judges choose the projects from the Biodesign Challenge. So how do you judge a student project coming through BDC? Well, we created a rubric which I used to think was a good example of a code. It's certainly based on questions, and we're always asking the students to consider these things, and we favor those who can actually articulate how they address these particular points. So originality, design, how effectively does the project respond to the topic posed? Is it scientifically feasible? Will it one day be scientifically feasible? Have the students considered how that might work? Or culturally feasible? You know, how does this technology enter into the world? For example, and this is a direct response to what we've seen with the ag tech companies, where they produce a technology, but it might not be culturally palatable. Similarly, we favor reflection. You know, how much did the team appraise what they were able to do versus what they weren't able to do? Can they get on stage and say, here's where we succeeded and here's where we failed? These were really important. I don't think this quite gets us to a code of ethics. I would say the most important bit, or one of the most important bits in this rubric is the context. So have you thought about who's using your technology? Have you thought about who doesn't get to use it? Is there an ethic or set of ethics embedded in the technology itself? Have you considered that? Questions of sustainability, questions of risk, right? Is it possible that someone might use this product that you're designing in ways you had not originally considered? Are there safety issues in their use? Are there safety issues in their manufacture or their disposal? All of these are sets of considerations. But again, this is the question is, you know, have you considered, not necessarily sort of a commandment of sorts. So as part of that issue in codes, we asked the readers to submit their own sets of codes of ethics. And I'm not going to read all of this to you, but I do want to show you some of the ideas that they came up with. You know, these for me seem to be quite aspirational as to the, I don't want to say the mood, but sort of the vibe of the community. Unity is very important. Interbeing with other species is very important to be considered. Humility, very important. Safety aspects, of course. And then, interestingly, the equality, not just among humans, but the equality between humans and other species, which is something that I think humanity has struggled with for a long time. I'll just read you the first one because I think it's quite lovely. To truly achieve a just, diverse, and equitable future, one that is necessary to protect our environment, biodesign cannot be disentangled from social justice. As the planet gets hotter and more crowded, biodesign can demonstrate how we are all interconnected. Biodesign has the potential to unify because the language of biology is universal. Biodesign offers a pathway to dismantle systems of exclusion and uplift us all. I think it's a powerful statement. How do you actualize that? How do you activate that in a code? These are the sorts of questions that we might want to ask. It's also a question for us as a community whether the ideas embedded in this statement belong in our code. So going back to Jason Bobe and the DIY Code of Ethics, the DIY Bio Code of Ethics, he asked us these questions before we even got started. And I think this is easily transposable to the world of biodesign. such that we might change, switch out the word DIY bio here and put in biodesign and see if it works. So what type of code will best suit biodesign at its current stage? Should we develop a single universal code, or should local groups have their own? Is a new code necessary, or should we augment an existing code that currently exists somewhere? What issues should it cover? Who belongs in that room? Who should be the people devising that code? Is it a code that you are going to enforce? Is there going to be a stick associated with this code? Or is it something that people voluntarily sign on to? What purposes are we trying to achieve with this code? And of course, how do we actually come to consensus around building such a code? All of those are important questions before you even get started. And I would argue that, there's an open question about whether this should be something that should be gotten started. And I think that's something that we as a community of biodesigners and biodesign advocates need to think about. Here's would be my prescription. And I don't want to be prescriptive too much in this environment, because I think, if we're going to be talking about codes of ethics, it needs to be done through consensus. And so I'm very nervous to put forward my own ideas before I hear others. But I will say two things. I think, we should be thinking about what is a rule for a practitioner. So what is a thou shalt not in this realm? And then what is the aspirations for the discipline? What are we hoping to achieve as a discipline? The types of criteria that you would come up with, what you put into this code, will look very different if you approach it from these two different ways. So, I would advocate for aspirations for a discipline. I think that biodesign has been around as a community that has named itself as such for about a decade. But I think there are a lot of open questions as to what it is we're hoping to achieve as a group. Setting those aspirations together, I think, will help us mature as a community. And so I'm going to put forward 3 suggestions for some of those aspirational goals, with the recognition that I'm just a member of the community, and therefore, this is not my sole decision. So I would argue that we need to think about design across species. Biodesigners propose creations that serve multiple species simultaneously, including but not exclusively humans. These might include microbiota of a certain place, or the biology of a certain place, but it also includes the wildlife impacted by the production and disposal of what it is we make. So that would be one principle: design for multiple species. 2, design across life and death cycles. Beyond designing for just industrial products where the end user is just us, the consumer. Let's start thinking about who's actually using those feedstocks, how those feedstocks are entering into the system, and then 2, who or what is using that waste when we no longer use it. When you start to think about a product as something that's being used before we are and after we are, I think we might design quite differently for what it is we make. Number 3, again, these are just 3 suggestions. Design for biological heterogeneity. In Evan and Margaret's talk, they talked about how, living things are not industrialized products. They don't all look identical. They don't all function identically. Because biodesigners often grow their materials using living substrates, they have begun to embrace, I hope they've begun to embrace, an aesthetic that defies contemporary industrial design. Just as we appreciate the heterogeneity of living things, biodesigners emphasize the uniqueness of each design object over the homogeneity of industrially manufactured goods. These would be my suggestions. All right, with that, I want to open up a dialogue, a discussion with the recognition that not everyone in the room comes from the biodesign community. Many, of course, are guests to the community. So all the same, I think all input is really welcome. With that, thank you.
Thanks, Dan. Thank you very much. Now we give space to a round of questions, Q&A.
Hi, thank you for your talk. I think that I always enjoyed discussing codes of conduct. I think they are very important. I'm a designer from Latin America, a grad student. And for me, joining academia in the United States, something that has always, or that has I started to wonder, is this idea of the academic weird, which is that a lot of academia is based on Western educated, industrialized, rich and democratic principles. And I was thinking about if that should be a consideration when talking about a code for biotechnology or biodesign as well, because a lot of our inspiration comes from, or our new discoveries are things that indigenous communities have been building for millennia. Adobe houses, my work with agave fibers, they are nothing new. They have been doing that for millennia. And that's something I wonder quite a lot.
I think the answer, I don't think I think that's a valuable comment. You know, it's a question of who considers themselves a biodesigner. I think it's true across a board that many biodesigners are influenced by indigenous practices. I'm thinking of Braiding Sweetgrass as an example, as a book that's an inspiration for a lot of our community members. You know, there's a question of, can indigenous communities be involved in this dialogue? Do they feel like this is the space that they belong in? I don't know the answer to that. I think it's a question of their own will. Certainly, it's something worth considering. It's also worth considering like who we are when we create codes, right? So if we're sitting in academia, we're going to have different pressures than people who are maybe sitting in industry. And so, yeah, I think doing this kind of work requires a kind of awareness that is quite difficult to do individually and often difficult to do as a group, but something that is important. And I would argue that, you know, when you do this kind of work, it might be worthwhile having a social scientist or several social scientists in the room that can provide a little bit of context or call you out when you're making assumptions that you don't even realize. And I would add another piece to that, which is that, you know, codes they don't have to be written in stone. They're only useful until they're not useful. And so, you know, these things should evolve and change.
Thank you.
Questions? So Dan, I have a question, or it's kind of a comment / question, because it's interesting what Diego was mentioning, and for me it's really important to bring many different disciplines into this conversation, right? So, and I think that your work on founding and directing the Biodesign Challenge really opens up the biodesign world for the rest of us. And then you yourself switching to a more lawmaking or policy making role already shows how the field is evolving. So my question would be, is there any discipline in particular that you would like to see more involved in the developing of the biodesign community?
Oh my gosh, that's a great question. Yeah, I think There are a couple. I would love to see more craftspeople in the world of biodesign. I think you're right when you say, hey, people have been using these materials long before, a bunch of, Western educated folks like myself have gotten involved. They have a very different relationship with the materials with which they work. And getting that perspective into the room will be very important. I think that would be number one. I already mentioned the social scientists. I think they're critical. I think part of the challenge when you create an interdisciplinary movement, I don't know what to call this. Is it a movement? Is it a community? Is it a discipline? You tell me. But when you create that, people are coming from different perspectives. And so what you need to be able to do is keep the language loose enough where people are still able to interpret through their own lens, but then sort of tight enough such that we're not just all talking about something vague. Meaning you want to be able to get experts and people with different disciplines talking to each other with the acknowledgement that they're going to interpret whatever it is you write, whatever code you create differently. And I think that's actually been something that has been fine-tuning that has been a significant challenge for biodesign, since its inception, right? We've always said, hey, we're going to have a group of judges and experts who are going to look at our rules, and we created our rules to be quite broad sounding, with the understanding that if we create the right balance of people in the room, their perspectives will balance as well. And honestly, sometimes that works and sometimes it doesn't work. What I don't want to see is that we get so rigid and so detailed that no one feels like they belong in that room. So how you play that balance is something that I think, again, it's tricky and it's going to take iteration to get there.
Okay, so there's one more question there.
Hello, Dan. So in the slides that you showed with the different codes, I never saw the word, if I read quickly enough, politics. And I think there's often assumptions, or whether it's politics or ideology or worldview frameworks like capitalism versus a socialist view, whatever that means. I'm just curious, when I think about biodesign, one of the things about the community that I've noticed so far, and it's a tension that has existed also within the Biodesign Challenge, is between teams that aim towards startups, whether they be nonprofits or whether they become actual for-profit companies doing good in the world, or getting so big that who knows what happens in the future. I think there's so many questions, I think, tied to underlying assumptions of maybe I'm not figuring out how to phrase my question. I'm forgetting my train of thought. But do we need to spell those out, those kinds of underlying thought assumptions in a code of ethics, or is it something that just happens through the community being diverse and those of us who participate talking and listening to each other to see where it goes? I mean, the goal is heterogeneity, so I'm not taking aside one or the other, but I'm just curious in your thoughts about codes.
I think you can create I think it's a great question. I think there are a lot of tensions built into Biodesign Challenge that we've recognized and decided to live with. When I showed you the sort of that graph with this speculative and actual and problem finding and problem solving, putting the people who problem find with the people who problem make or problem find and problem solve in that room, like, it is inherently a tension, right? And they should be arguing, and there should be critique, and there should be some levity in the room so that you can take that critique, and there should be some self-awareness to know when, hey, I hadn't thought about that, maybe I need to rethink what I'm proposing. It's really hard. I think that if you want to have a group of people together who are thinking about applications of a technology that is both exciting and quite scary, a technology that, you know, has the potential to maybe solve some of our sustainability issues, but also could run rampant. And, you know, you can imagine releasing, you know, the green goo into the world. You have to do it very slowly, and you have to do it judiciously. So I want us to be able to say, hey, we all are, you know, we all are represented under this one flag, with the acknowledgement that there's a sort of an inbuilt system of critique, that we are proposing things and also critiquing those things at the same time. And how do you do that in a way where it doesn't feel like you are always backbiting, or you're always taking 2 steps backwards, and when you take 1 step forward, is something that I think we need to figure out as a community. Number 2, I think that we've been around now for over a decade as a community, or roughly around a decade as a community. The codes are effective communications tools in the sense that it advertises who you are and what you believe. And it allows for new people to come and enter into that community because they can sign on to that set of codes. If there is no set of codes, people will come, but it's always a little bit vague about what you guys are about, what it is we think we're doing. And I think that's a real problem for the biodesign community. And I think it's a problem in the sense that essentially, you know, ideological trends come and go. And if you don't have some sort of code, you're just going to go with the wind. And it's going to be kind of this wishy-washy community. And what I'd like us to say is, hey, this is what we stand for. And when we do our research illustrates those actual principles. I guess now I'm advocating for a code, but next week I'll advocate for why we shouldn't have a code. So watch out. But I think we as a community, we're mature enough that we can create this. Number 2, I think that you're right. Like, there are tremendous industry capitalist pressures on this community. It's the nature of the fact that we are working with a community of students who are about to go into the job market and have valuable ideas to people out there who have a lot of money. And so if you don't set those principles at the very beginning, then my fear is that they're just going to get carried away by those capitalist impulses. And what you had originally intended for them, or what they had originally intended for themselves, will be lost.
Yeah, I really appreciate that. I think you've done a great job in the biodesign community, from all of your efforts, but also through the competition, to keep that open and to let the different points of view be heard. It's something that is often difficult to do in the university because of the academic silos. You know, the scientists might work, but then the science, technology, studies critics might be in a different humanities department. It's kind of like the old divide of sciences versus arts and humanities. And yet you've bridged them by putting bio and design together into the same word and into the same community. So I just want to say thank you. So.
Well, well, thank you. Christina's one of our, I don't know, all-star professors. I just want to add to what you're saying, you know, like once a year, when those who can fly to New York, you know, with their students, we have this wonderful moment when the barriers between design and technology and social scientists sort of come down. And the second everyone goes back home, they go back up. And so there's an opportunity at that point for us to build on what we've already been building. We have a community that's interdisciplinary. What can we do to actually strengthen ourselves and our own practices? And what can we do to strengthen the community? I think that's a question for us who show up in that room. Now, I want to say that that's a problem, because those who show up at the Museum of Modern Art in New York City, those are the ones with resources. And that's, you know, those are the ones who can afford that flight. They're the ones who can afford a hotel room. But they shouldn't be the only ones who are making this decision for our community. ask me how to do that, how to fix that problem. I don't know. We've, you know, for the last couple of years, we've been in BDC, we've done BDC online. It is a totally different experience. I would say it's a shell of what it is when we're in person. And so how you bring everyone together to have these conversations, again, another open question, but it's one that we need to really nail down.
Great, done. Thanks a lot. Again, we are and will continue to experiment. We are experimenting and will continue to experiment this week. I think it's very important. Margaret and Eman's talk about the industry and your talk about the code of ethos. I think it all builds up. I'm prone to using the word industry because I think that's what it should become in order to better approach or tackle all these problems. And I think that complex problems require interdisciplinary solutions. And having a code of ethos and having people like you pushing this forward really gives the foundation for the rest of us who would be scientists and experimenters. So thank you very much for that.
Thank you. And thank you. Thank you all for your ear and your comments. I'm hoping that ideas will percolate over the next couple of days. I would love to hear any of your thoughts. That goes for everyone in the room. We're very much trying to still figure out our identity. You know, we're adolescents here. And so any insight would be greatly appreciated. Thank you all for listening. I'll hopefully see you soon.